My name is Chris Sanders, and this is an analytic plan that I would like to propose to Dr. Schueller at Northwestern University and Dr. Parks at Hiram College as a way of analyzing the data in dataset codenamed packages. So while this is a complicated analytic plan, it can in its entirety be broken down into these three simple steps. The first two are descriptive, the third one is inferential, you'll notice. And basically all we're going to do is in step one, create a trend line to represent each one of our participants. Step two, we're just going to group those trend lines together to create meaningful groups. And then in step three, we're going to run appropriate analyses to determine group membership based on our set of predictors. A lot of this was built from the ground up, so I'm going to go into the details of now. Alright, step one. This is just adding a trend line for each individual participant. The data, as you'll know, is longitudinal in nature. I have pre-test measures, post-test measures, 1 month follow-up, 3 months, 6 months, and 1 year after the intervention period. And so we can draw trends along that time period in order to create meaningful stories out of the data. We have a couple of objectives going in when we're doing our intra-individual polynomial modeling. That's technically what this is called. We want to focus on preserving as much information about each individual as possible. We also want to preserve subjective well-being as separable concepts instead of relying on just a unidimensional model that just collapses all the different concepts of subjective well-being down to one variable. And we want to respect the known limitations of our data. This is kind of an intricate point, but I'll get into that at the end of this section. So to start off, I'm going to talk to you very briefly about information preservation. This is sometimes referred to as taking a person-oriented approach, but in the current analysis, we want to preserve as much information about each individual participant as we can for as long as we can in the analysis. So that's why we end up actually with 2 descriptive steps to begin the analysis and a 3rd inferential step just to wrap it up. The strengths of descriptive statistics are that there's no worry of alpha inflation, so you really, as the researcher, have the power to explore every little aspect of the data that you'd like to see to a certain extent and model it however you best can with the mathematics of your time. As soon as you take that step over from descriptives to inferentials, you're tremendously limited in your ability to mess around with this data any longer, all because of that alpha rate inflation problem. And so by the time any researcher, statistician, gets to the step of performing inferential stats, they should already be very well familiar with their data through descriptive processes. Though this is stuff that everyone here already knows. Additionally, we'd like to preserve a multi-dimensional look on subjective well-being, rather than reduce it down to a univariate model. To do this, all we have to do is keep our life satisfaction measures separate from our affective measures when we go through the analyses. So whenever we're talking about our dependent variable subjective well-being, we are simultaneously talking about these 2 separable, though intercorrelated, constructs. For specific mathematical reasons, I've chosen to use polynomial functions to represent individual trend lines over time in both life satisfaction and affect balance. In this next video, I'll explain to you some of the components of those polynomial functions and tie in a major limitation that we have assumed right off the bat. Here's a two-dimensional way to look at our data. Take either one of the two dependent variables, so affect balance or life satisfaction, and place it on the y-axis, and place time on the x-axis. And in our case, the time is going to be that span of time where we were gathering data from the pre-test to the 1-year follow-up. The next thing that you would do is just place down a couple of data points that you would have from any given individual. And you can see that with these 2 points, it's possible to draw a straight line that passes through both of them, a line that has a y-intercept and a slope, simply. You would call this a saturated model, or a polynomial raised to the d-1 degree. Now, if we add a third point in here, it's impossible to draw a straight line that passes through all three. So the thing that we would do is raise this to a second degree polynomial function. And now there is an intercept, a constant slope, and a quadratic slope. And we, again, are calling this a polynomial to the d-1 power saturated model. Add in a fourth data point, and so you would raise this to a third degree polynomial. So this is that d-1 part. 4 data points means that you raise it to the third degree. 3 data points means you raise it to the second degree, whereas 2 means you raise it to the first degree. In our current set, we have 6 possible points for data collection. So the largest saturated polynomial model for those 6 points, squiggly line that passed through all 6 of them, would be a 5th degree polynomial. We decided a priori that there would be certain inclusion criteria for an individual's data set on a given dependent variable. And based on that, we'll end up having people who have 4, 5, and 6 data points for each one of their dependent variables going into this. Those will be the people that get retained in our analysis. Now there's a striking problem to having a saturated model in that we know going into this that all of the individual data points are good representations of where a person's affect or satisfaction with life is at a given point, but it's certainly not a perfect predictor. And so at the very most, these data points should only be able to characterize broader trends amongst themselves rather than a line that is so squiggly that it passes cleanly through each one. Previous slide, we raised our polynomials to the d-1 degree in order to make them saturated lines, ones that perfectly represent each one of the data points. In order to make them smoother lines that are less immediately representative, but ultimately, theoretically, more representative of the actual trend, you'd raise this to a polynomial function of a degree of d-2 instead of d-1. So in the previous example, if we had 4 separate data points, instead of raising that to a third degree polynomial function as you would in a saturated model, you raise it to a second degree. And the same sort of logic applies for all the data points that fall after it. So a 4th degree polynomial function would be one that represents all 6 of those data points. And so you see that for each individual participant and each dependent variable within that participant, we have a set of coefficients here that will represent their individual trend line over time. And later on, we'll use this information in grouping our participants together. So in this step, all we are doing is generating a line intra-individually that represents each individual person. in their own unique way. Now, regression is the process that you would use to form this line that represents an individual. And up here you see the typical linear regression model, where you have a set of coefficients and you have a set of predictors and some sort of outcome variable that you're estimating based on those predictors. So it turns into a very similar equation to our polynomials that we've been working with, whereas you have a beta sub 0 coefficient that represents the y-intercept, and then you have a beta sub 1, beta sub 2, beta sub 3, and so on that match up with each one of the individual predictors in your model. Now, recall that with a maximum of 6 data points per person, the largest function that we're going to generate is going to be a 4th degree polynomial function. And so if you were to do such a thing in SPSS or another statistical software package, you would end up with something along the lines of the table that you see here, where it just lists out the unstandardized beta coefficients, and if you took those beta coefficients and plugged them back into the regression line up above, they would actually be useful in generating whatever the target variable is. In our same case, this 4th degree polynomial equation matches up exactly with the regression equation above, just substituting in x to the 1st through x to the 4th power in for the 4 different predictors. The exact same process happens over again, and you end up deriving that line that you're looking for, the line that represents the individual in the exact way that you would like it to. Here's something I call the toy. A couple of weeks ago, I ran the regression equations to figure out the intra-individual trend lines in satisfaction with life and affect balance, and I can present to you a graphical representation here of what we have so far. One small caveat to interpreting these graphs is that I did not mean center the prediction variable when performing the regression, and in later iterations I will perform this mean centering, maybe to the extent of making a negligible change to some of these lines, though it's good practice and slightly more accurate than the procedure that I used to construct them right here. Without further ado, right in front of you, you can see 2 graphs, one for life satisfaction, one for affect balance. And I'm going to scroll down so that we can see both of them at the same time. 530 participants qualified for our analysis, and these are their individual data points at the 6 time points in our series. So the leftmost column is pre-test, the next is post-test, 1 month, 3 month, 6 month, and 1 year follow-up to make up the 6 lines left to right. So if we were just going to draw a line across these 530 participants, it would look something like this. Now, if you could also visualize this as a 3-dimensional line, but it's really easy to see here as 2 2-dimensional lines on separate plots. Anyways, to note, not much changes. Actually, affect balance seems to go down just a little bit over the course of that year and 6 weeks. While satisfaction with life, maybe in a curvilinear way, increased just a little bit. What type of information we lose, however, when just looking at broad generalizations across this huge set of people, is the individual lines. This is why we're taking a person-oriented approach starting off this analysis. So the individual line for each person maps out something like this. Now I'm also going to put down the time point markers so that you can see the reasonable range of the data. So within each scale, satisfaction with life ranges from 5 to 35. Affect balance, I believe, runs from 40 to negative 40, though it's cropped off at the bottom because that is where we drew our inclusion criteria for any individual observation, which is plus or minus 3 standard deviations from the mean. Okay, but I did want to take these lines off real quick, and I'll take off the individual points, and so you can see that representation here. The full range of observed values is going to be the vertical lines in each one of these two graphs, while the range of the graph itself, the area that you're observing, is going to be the range between negative 3 and positive 3 standard deviations of the mean across this entire variable. So make this colorful and interesting one more time. Slap down each one of the individual lines, and you see that they're all over the place. While the mean line across this entire range is pretty static, the individual lines bounce everywhere, and so they may be good candidates for clustering in this type of way. If we reduce the range of participants that we're viewing down to something smaller, it becomes a little bit easier to see what each one of these lines looks like. This is a completely arbitrary distinction, of course, in the participants that we're currently viewing. Those are just the 25th through 48th participants to qualify for this. If you'd like to see their original participant ID as it was coded in the original data set, I have a searchable function right here that limits itself down only to the line that's being observed. And so you can see that right here. If you'd like to play with this toy, just let me know and I will send you the R code for it. Thank you very much. So we enter into step 2 of our analysis with a collection of trend lines that represent our participants. And our next step is to reduce this collection down to a reasonable number of prototypical trends so that we can interpretate them easily. When we do this reduction, we have a set here of firm objectives that we'd like to achieve in that clustering. So the first one here, for purposes of interpretation, we would like this to be reduced down to prototypes so that I can take this small collection of prototypes and describe each one of those individually and use it as a point of explanation of what has happened to the participants. The next 2 points add towards the accuracy of these prototypes that we're creating. So the trends should be distinguished by their line shape. That means that the individual participant trends as well as the prototypical trends should all be represented by the shape of their line. And that whenever possible, we should avoid arbitrariness in our decisions. The final objective on this page is that the procedure should detect change. So there should be some way, because we're looking for people who have benefited, there should be some sort of way to demonstrate the distinctiveness of an individual's benefit across this time, or more specifically, a prototype's benefit across this time. Because this is a prototypical clustering approach, the foundation of our analysis is going to be the k-means clustering solution, and I'll explain that right here. The k-means cluster solution in under 2 minutes. The objective of the k-means algorithm is to find a user-defined number of prototypes that best represent the data set. So if we had 2 variables that we were interested in studying, we could plot them on a scatter plot just like this, with all of these data points representing individual level data. And to begin the k-means algorithm, we would start off by randomly assigning, in this case, let's say 4 different prototypes, just random numbers that fall within the range of the data. Now, the first step of the algorithm is that you calculate the distance between each one of those prototypes and all of the different points on that scatter plot, and you assign points to prototypes based on which ones are closest to that prototype. Then you just recalculate the prototype as a mean of all those data points. So the prototype is a better prototype of that group, if you will, or that cluster. And then you repeat the same process over again with the previous step and figure out which points are now closest to that new prototype now that it's moved. And you continue doing this iterative process over and over again until the solution is found that the prototypes no longer move. And that is the k-means cluster solution in a nutshell. To recap, the k-means algorithm works like this. You take a user-defined space and you start off by assigning a set of user-defined random prototypes, just random numbers that fall within that space that you've already defined. In our present case, we're going to try this out with 2, 3, 4, and 5 prototypes and then compare those to one another in order to find out which one of the k-means solutions is most appropriate for our current data. But once you have this space defined and your initial prototypes thrown down, then you enter into the iterative portion of the algorithm. And this iterative portion is really the engine behind it, and you have the 2 components here. First portion is just assigning individuals 2 prototypes, and you do this by calculating the distance between each individual and each prototype. This part actually becomes a little bit complicated for our present case, but I'll get into that in the next slide. And then the second step is that you just recalculate each one of the prototypes so that it is a better representation of all the participants that's within its set. And we'll get into that further as well. For efficiency, from here on out, I'm going to refer to the prototypes as K and the participant trend lines as P. If we put this all together into our own algorithm based on the k-means process, first we would assign our individual k's, and we'll do this process actually for a number of reasonable k's. But once we've established these random prototypes, they're just going to be any random function within our range. We start the algorithm by calculating that distance. So this is the first step of the k-means process. And our step involves finding the curve similarity between the different lines, because that's actually what's important in our grouping. Next, we assign each one of those lines to the prototype that they're most similar to, whatever function they're most similar to out of our list of given prototypes. And then step 2 of the algorithm, we just recalculate the prototypes over again as a mean of the p points, and keep on doing this algorithm until k's no longer change. And there's also another step that you can add in here in case of a never-ending loop, so that it only runs for a certain number of iterations and doesn't break your computer. In this slide, I'm going to dig even further into the very first step in our algorithm, the distance function that we're calculating between each p and each k. This distance function can be broken up into 3 phases. The first and third phases are from calculus, and the second one is from simple geometry. So this portion of the talk, I'm going to step away from psychology and statistics to just talk about a little bit of math and let you know how we arrived at the function used to calculate curve similarity between 2 different lines, rather than the distance between 2 different points. So recall that this is the way that we're going to distinguish which one of the prototypes each one of our participants fits into. So which one's curve matches best. So to start off of phase 1, we take each one of the functions that's used to represent each one of the p's, and we find the derivative of that function. What that does for us is it gives us a new function that represents at any given point along time, our x-axis. You can use the derivative function to find the exact linear slope of your original function at that point. So in the picture you can see that at that given point on that curved line, we can calculate using the derivative the exact slope right there. So now each participant and each prototype has been reduced to this rate of change function rather than their original functions. We then calculate distance by subtracting this rate of change formula for each participant from the same rate of change formula for each one of the prototypes. And so now we end up actually with a function. This is kind of a hard topic to follow abstractly, but what we actually produce is a function that represents the difference between the slope of each participant and each prototype. Recall also that we're measuring subjective well-being in terms of both affect balance and life satisfaction. So if affect balance is the y-axis, life satisfaction is the z-axis. Again, time is our x-axis through all these analyses. The way we would collapse this down from a more complicated 3-dimensional picture to a more simpler 2-dimensional picture is through a Pythagorean transformation. So you learn this in high school. It's a squared plus b squared equals c squared. And from phase 1, we have a function that represents the distance between the slope of p and the slope of k for the entire span of time that we're measuring on our x-axis. And we have that for both life satisfaction, one of those, and one of those for affect balance. And so in calculating the distance that a person differs in their slope based on both of these 2 dimensions would be something that travels diagonally across those dimensions and measures that distance. Now we have, for every kp pairing, a single function So every time I'm talking about function, I'm talking about y equals b sub 0 plus b sub 1 times x, and so on. It may be polynomial, it may not. But where we're at right now is that we have one of these functions for every kp pairing. And if we want to take a sum of that function for the time period that we're interested in, so we are making the decision to limit our analysis only to the data that we have in front of us. So we start our period of time, which is the x-axis. We start that at the pretest, and we end that at the 1-year follow-up. And we find the sum difference in slope between every p and every k by taking this limited integral to calculate that space. Now, thankfully, the next step in the k-means algorithm is much simpler, and I can explain it here. It's simply you just take a mean of the functions p that are within each k, and that mean function is your new k. It's your new prototype. It's a squiggly line traveling through space that best matches the squiggly lines in its group. Now, the only thing that I have left out so far about this clustering process is that we have a final objective of finding lines that are distinguished from no change. That's just another way of saying that we are looking for people who change, specifically because we're trying to identify benefiters. And we're expecting also to find people who get worse over that time span for one reason or another. So the final little bit that I'm going to add on to this algorithm is that one of our k's is going to be set to a null hypothesis. So this is a flat line with 0 for all of its coefficients in both dimensions, life satisfaction and affect balance, that does not change. So this prototype, as it goes through, will continue to collect lines that are similar to it, and will also provide a certain degree of distinctiveness between that null hypothesis and any other group. And here's our final step. Now we have a single dependent variable, and it's just cluster membership. We'll make some sort of interpretation of what each cluster's trends looks like, and we'll be able to do so by comparing it to the null hypothesis trend. But so single univariate nominal dependent variable, and from there we can test out all of our independent variables that we're interested in the packages dataset. So this dataset has demographic information, it has all sorts of information about an individual's mental health history. It has their depression scores over time measured at multiple different points, and some interesting stuff about what a person was thinking and feeling while they were going through the intervention, like did they enjoy it or did they find it difficult. And it also has their adherence and continuation of the intervention behavior within and after the intervention period. So when we have the case of a categorical dependent variable and a set of independent variables that are both continuous and categorical and have all sorts of different stuff going on with them, we can use these two strategies, descriptive discriminant analysis and logistic regression, to find the statistical inferences about the relationship between the IVs and the DVs, or the single dependent variable. The discriminant analysis is the more powerful of these two analyses, though it contains within it a lot of assumptions about normality and multicollinearity and things like that. Though it is regarded to be a robust test, just so long as we make sure to handle our multivariate outliers well. Logistic regression, on the other hand, has fewer assumptions than discriminant analysis, and it's also less powerful, so it's less able to find effects, but it does provide us with a easy to interpret effect size, something that translates to a person's probability of changing from one cluster to a different cluster based on their response to an independent variable. So these three steps together, first, assigning a squiggly line to each individual participant. Number two, grouping those squiggly lines together into reasonable prototypes. And then step three, making inferences about prototype membership based on our independent variables. Those three things coming together is my analytic plan for handling the package's data, and I would like to know what you think. Thank you.